afternoon, is Krishnaveni Parvataneni. You're going to tell us about investigating rotational and vibrational temperatures of a DVD plasma jet for medical application. I don't know what that means, and I'm dying to find out.
Hi everyone, my name is Krishnaveni, and along with Dr. Zaidi from San Jose State University, I've been working on an investigation of the rotational and vibrational temperatures of a dielectric barrier discharged plasma jet for wind killing and sterilization. So plasma is the fourth state of matter. It's basically ionized gas, and it usually occurs at very high temperatures, but it must satisfy a couple more conditions than that, including a thing called debioling and a number of oscillations that I won't go too much into in this presentation. There are two major kinds of plasma. There's thermal plasma, which is at thermal equilibrium, which means that the electrons and particles are at the same temperature. And there's non-thermal, non-equilibrium plasma, which has ions and neutrals at a low temperature, but electrons at a high temperature. And DVD plasma, or dielectric barrier discharge plasma, is non-thermal, and it's used in medical applications because it has generally low temperatures. So for our experiment, we decided to use a multi-electrode plasma jet designed with two electrodes separated by a dielectric material. So that over there on the bottom right of this presentation is the multi-electrode plasma torch, and this over here is a good representation of how the separation of dielectric material goes. So we have over here this is our dielectric material, and on both sides we have an electrode, and this is the plasma that's coming out. So there are two main schools of thought for how wind interaction and plasmas work. The first is that the reactive atomic oxygen produced by the dielectric barrier discharge plasma it'll react with the water in human blood, and that will produce hydrogen peroxide. And that hydrogen peroxide will then dissolve into tissues, and that increases the oxygen tension of the tissue as a whole, which allows for the creation of fibroblasts and platelet-derived growth factors, and that would induce cell division and thus wind killing and sterilization. The other idea is that radicals in plasma directly lead to the formation of cell mediators such as nitrogen monoxide, and that would support the healing mechanism. So in the current research, we've been investigating the plasma's vibrational and rotational temperatures at various operating conditions in order to find the most ideal operating condition that would give an optimized performance for wind killing and sterilization. And to do that, we've conducted emission spectroscopy and used the SCCUR software to extract the information on the vibrational and rotational temperatures. Overall, we've used a DVD plasma torch with an electrical circuit, and that should be like a DVD multi-electrode plasma torch. We've used helium as our working gas and flow meters to basically control the flow of helium, and ocean optics UV-IR spectrometer to get the data from the plasma itself on the different it's like an emission spectrum that comes from the plasma. Then we also use an Arduino microprocessor to understand the temperatures of the plasma, and that was presented in previous research. And then we also use the SCCUR software to analyze data from the spectrometer. So over here, this is kind of like a design of how our torch works. So over here we have a DVD plasma torch, which is it's generating the plasma jet from the torch, and it's currently connected to the lower electrode, it looks like. And over here we have the circuit that allows electricity to go into the plasma torch. So we input a 5 kilovolt voltage, which is around 30 kilohertz of frequency, into the plasma torch, and we pass that through a 1000 to 1 high voltage probe to reduce the amount of voltage that goes directly into the plasma jet. And because our plasma jet is basically two electrodes over here separated by a dielectric material, which it's like that tiny rod up there, if you can see that. So because we have that, it's able to produce plasma over here, and then we go through one more 1001 high voltage probe, and the oscilloscope shows the voltage. So here's a typical radical emission spectrum. It's kind of what you'd see when you did spectroscopy on a helium plasma. And what we've done, we've decided to go through the interval from 350 to 400 nanometers, which includes the N2 second positive system and the N2 2 molecular line. And so those are the two transitions that we were most focused on. So in SCCUR, what we did, we basically calculated and fit plasma spectra based on a trapezoidal split function, multiple transition lines like the N2 SPS and the N2 2 molecular line, as I was talking about over here. And we used a main line at 336.91 nanometers. That was like our most important transition line. And the SCCUR software basically allowed us to fit new experimental curves to our original curve from the spectrometer to estimate the vibrational and rotational temperatures. So I'm going to show you a couple of the results we got from SCCUR. And all of them, this light blue line over here, is the emitted intensity. It's what we got from the spectrometer. And then we did various fits on this line at different temperatures. And for example, for this graph, this line, the gray line, is the best fit for that graph. So I'm going to show you 4 different conditions. This one is the lower electrode, 5 kilovolts, 5 millimeters from the 5 millimeters from the plasma jet exit, and 25 cubic feet per hour of helium inputted. So what that means is that, for example, over here, we're connecting the plasma, we're connecting the voltage over here into the lower electrode to generate the plasma. And if I said upper electrode, that would be like over here in the upper electrode. Okay. So over here, for the lower electrode at 5 millimeters from the plasma jet exit, we found that 700 Kelvin and 2800 Kelvin, 700 being for the rotational and vibrational temperatures, and 2800 being for the excitational temperature, was the best fit for our curve. For the lower electrode at 10 millimeters from the plasma jet exit, we found that 600 Kelvin for the rotational and vibrational temperatures, and 3000 for the excitational temperatures was the best fit for our curve. For the upper electrode at 5 millimeters from the plasma jet exit, we found that TR equals TV, so the rotational temperature equals the vibrational temperature, equals 600 Kelvin, and 3000 Kelvin for the excitational temperature were generally like the best fit. And then for the upper electrode at 10 millimeters from the plasma jet exit, 500 Kelvin for the rotational and vibrational temperatures, and 3000 Kelvin for the excitational temperatures were the best fit. So here's like a summary of whatever I just told you. As we got closer to the plasma jet, we'd see that there was an increase in temperatures, both rotational and vibrational. The excitational temperatures tended to stay the same throughout. In the lower electrode, the temperatures are generally higher than they were in the upper electrode. And as we got closer to the plasma jet exit, there was like a region in which the plasma temperatures became very unstable, and that was when the plasma arced. So overall, what we've done, we've created various plasma jets at different operating conditions, and emission spectroscopy was conducted on all those, and we used SCCUR to analyze the peaks to understand information on plasma temperatures. And in the future, we plan to work with E. coli bacteria cultures, and we're currently doing that right now in the lab. And we're also planning on exploring possible methodologies for the wound healing process. I'd like to take a minute to thank Dr. Zaidi, my principal investigator for this project, who's provided me with the information, the resources, and all the materials needed to go through this project. And thank you all so much for listening, and please let me know if you have any questions.
Could you go back to the future work? Yeah. What are those possible methodologies? Because I'm curious how you could heal the wound. I know you said that the plasma could be used for wound healing, but at the temperature you're talking about, I feel like it's a little high.
Yes, so we're going to start off with the E. coli and see how the E. coli works. Hopefully with the E. coli we can narrow down like a specific temperature a specific condition that might be the best for the sterilization. And then once we do that, we might work with like mice first, or some kind of laboratory organism that isn't a human, that is easier to perform research on. And from there, we're gonna try to like optimize it and then go to humans. But also, this is just like less than a minute of exposure. So, and it's been tested on human patients before, not by us, but by other researchers. So it's not anything that's like new or anything that's gonna like gravely worsen the patient's condition.
If you go to your last table, I think, where you should be at this one. So I was just trying to say, so when the distance gets longer, the lower electrode temperature is lower, but the upper electrode is higher.
No, in general, when the distance from the plasma jet exit is longer, so we did it in increments of 5, so 5, 10, all the way to 35 millimeters. So as we go from 5 to 35 in both electrodes, the temperatures will decrease. But as you go from the upper electrode to the lower electrode, so since the lower electrode is closer to the exit,
Right.
you'll have it as basically there's a higher temperature once it comes out of the lower electrode.
Okay, I see. Okay, cool. Well, they're still very high temperature.
Yes.
That's awesome. Very nice setup. I think that's really clever. Did you guys all design that?
Yeah, so this the multi-electrode plasma torch we've used, it's designed in our lab. And we also designed a couple of other torches that we're planning to test in the setting as well.
Awesome. Very cool. Other questions?
Wait, so you mentioned how like it can produce like hydrogen peroxide in your blood, like maybe more like nitrogen monoxide to like further like wound healing and stuff. But like, how exactly do you like, I guess, implement this on like a human, like in theory, I guess?
I guess like you'd have in theory if instead of this it would be like my finger, for example. Basically if the wound was my finger, the wound would be somewhere around here or somewhere around here, and the plasma would be like going kind of like scanning the wound. And we I think there's a separate project that's doing that. There's a separate project that's like working on MATLAB to scan the wound surface and then like make sure the plasma goes through all of it. But yeah, that's kind of how you do that. Yeah.
For the purposes that you're doing this research on, like what's the current clinical procedure for achieving the same thing?
For wound sterilization, it's just like, I guess it would just be like sterilizing the wound with like alcohol-based substances. And for wound healing, stitches, sutures, staples, or just like letting it heal on its own if it's small enough.
So is there a benefit if this with this sort of method?
It takes much less time to do it. It's like half a minute compared to like, for example, stitches or staples that take like 10-20 minutes to do. This is like half a minute of scanning. And yeah, this is like half a minute of scanning, and give me like 1 second. It's like significantly less pain because, I mean, it's a high temperature, but that's kind of why we're trying to find the best place for it. So it's like less time equals less pain. Like stitches, you have to go through that pain without anesthesia for the most part. But with this, it would just be like half a minute of pain max.
And then